I'm going to run you through the nucleophilic substitution reaction mechanism, showing you the reactions which occur with hydroxide ions, cyanide ions, and lastly ammonia. It's always useful to bear in mind what various words mean. So what is a nucleophile? Why is it called nucleophilic substitution? It's because a nucleophile is an electron pair donor. So examples of nucleophiles include OH-, CN- and NH3, ammonia. Nucleophilic substitution reactions involve halogenoalkanes. I'm going to take you through an example of the hydroxide ions reacting with bromoethane. So there's your halogenoalkane. And you want to follow these steps when you're asked to outline the mechanism. So we'll start with the displayed formula bromoethane. There's 2 carbons. We have a bromine attached. I'm going to complete with hydrogens. We now need to add our nucleophile, which I've just told you is the OH-. Do make sure you show the lone pair of electrons on the OH-. The next important thing is to show the fact that the bromine here is electron rich, so it's delta negative. This means that the carbon here is electron deficient, so it's delta positive. You must always draw curly arrows here, and it must start from the lone pair, and it's attacking the carbon here. This causes the breakage of this bond, and so we can now draw the second stage of the mechanism. The bromine has been substituted for the OH, hence the name of this mechanism, nucleophilic substitution. We've lost this bromine here, so we need to draw it as the product, and it has a lone pair of electrons. We've taken our bromoethane, and actually what we've done here is produced an alcohol, which is ethanol. They might ask you about various reaction conditions. With hydroxide ions, you need aqueous ethanol to be used as a solvent. This time we're looking at cyanide ions and chloroethane. So a second example of nucleophilic substitution. It's very similar from what we've just done. We'll start with the chloroethane. This time we've got a slightly negative chlorine, a slightly positive carbon. Let's show the cyanide ion. Remember, that is a triple bond. It has a lone pair here. It's negatively charged. We know the lone pair will attack at this electron deficient carbon, causing the breakage of this bond. Draw the new product form. In terms of naming, we have gone from chloroethane, but look here, we now have 3 carbons, so the carbon chain has increased. So we have propane. And then remember, it's very important when you're naming nitriles, you include that E. So we have propane nitrile over here. You might be asked about the source of the cyanide ions. These are produced by potassium cyanide in aqueous ethanol. I will write that here for you. We avoid using hydrogen cyanide because it produces a toxic gas. And then our third example of nucleophilic substitution is this time with ammonia. I'm going to take chloroethane as my halogenoalkane. In terms of conditions, we need excess concentrated ammonia in ethanol. The reason why it needs to be in excess is to minimize further substitution occurring. So let's show the mechanism. Here's chloroethane. Here's my slightly negative chlorine, slightly positive carbon. Let's show the bonds on the ammonia. There's no charge, it's neutral, but it does have that lone pair. That's going to attack the slightly positive carbon, causing the breakage of this bond here. And then this nitrogen is positive. We can't leave it like this, so that's why the excess ammonia is needed. The lone pair is going to attack one of the hydrogens. Doesn't matter which one, causing the breakage of that bond to form this is the final product. So we've lost one of the hydrogens. We have an NH4+ and ammonium ion left over, as well as a halide ion. This could also be represented as an ionic compound like this. So be warned. What is the name of this substance? It's got 2 carbons. It's got an amine group. It's ethylamine. The reason why this is a slightly different example compared with the two above is because before you had a negative ion donating an electron and therefore becoming neutral, as we see here, whereas here you have a neutral molecule, ammonia, which donates an electron pair, and that's why it becomes positively charged. So it is important that you're aware that each step of a reaction mechanism must balance, both in terms of atoms and charges. Bromoethane reacts with potassium cyanide to form compound D. Outline the mechanism for this reaction. Remember that this is a nucleophilic substitution reaction. It's important you know the name of the reaction because it will help when it comes to drawing out your mechanism. So I'm going to draw the displayed formula of the bromoethane to make it easier to see. Here's your all-important nucleophile with that lone pair of electrons, which is going to do the attacking. Label your electron-deficient carbon, your electron-rich bromine, and then show the lone pair attacking the electron-deficient carbon. So there's my curly arrow, and that's going to cause the breakage of this bond here. This allows the CN to join and replace the Br. You can see very clearly here that the carbon chain has increased in length by 1, and we'll have a Br minus left over with a lone pair. Now we need to name this. So as I've already said, we have 3 carbons. This here represents a nitrile, so we have simply propane nitrile. Don't forget that you've got to put that E in there. That's the difficult thing when it comes to naming nitriles. 2-methyl-propan-1-ol can be prepared by reacting 1-bromo-2-methyl-propane with dilute aqueous sodium hydroxide. Name and outline the mechanism. Again, we have nucleophilic substitution. Be very careful. Here's your reactant. So start with your 3 carbons. We know we have a Br group on the first carbon. We know we have a methyl group on the second carbon. I'm just going to draw it like that because it won't be involved in the reaction. I'm going to complete my hydrogens. Now I'm going to draw my nucleophile, the OH, minus. There's the lone pair. There's my slightly positive carbon, slightly negative bromine. We know the lone pair will attack the slightly positive carbon, causing the breakage of this bond. The hydroxide adds itself. The rest of the molecule remains unchanged. And we're left with a Br minus.